All right, go ahead and start with a quick intro on just what is digital money. Most of us already know what that is. I mean, we all know what a register is. We all know what our bank account is. But most of everything we interact with is digital. We got our paycheck, ACH transfer from our job. We get paid as digital. All our debit card transactions are digital. So, for all intents and purposes, whether you believe in crypto or not, you do believe in digital money because that's exactly what we're doing. We don't have to interact in cash unless we need to. Everything we do is digital. The difference is that it's on a system, a banking system, some type of system that we inherently trust. And that's the key. This is a ledger. Our bank is an app and an institution that we trust implicitly. So that begs the question, what is Bitcoin? I mean, you go on Coinbase, you go on some exchange, you go ahead and deposit money. You can go buy $20 in Bitcoin right now. It'll do an ACH transfer from your bank account. And what are you getting? Warren Buffett would say you're getting nothing, but that's not true. So what are you getting? Well, a transaction is made. Of course, as soon as you get paid from an exchange, you should immediately transfer it to your own wallet. So in this case, if I transfer it from my wallet, I'd put an address and the exchange would transfer me money. Let's say I bought one Bitcoin because, I just had an extra $30,000 laying around. This is what it would look like. All right. This is what's called a UTXO. This is an unspent transaction output. All right. So this is a transaction in this box. This is the transaction ID. I just made it something simple. Usually it's a really long string of characters. I just made it ABC456, And you always have an input. An input is just an output of another transaction, which I'll show you in a second. And then there's the output. There's an amount, and then there's an address. That's it. So if you see another one like this, so let's say this is my address with one Bitcoin, and I want to pay my friend Bob one Bitcoin. Well, I would construct this transaction here. You see the input is ABC456, and the output number is 0. Because remember, computers don't start counting at 1. I know it's annoying for you non-computer programming people, but computers always start counting at 0, And then there's the output, and there's my friend's address. So you can see these UTXOs, or unspent transaction outputs, are always linked together. Now, of course, you can have multiple inputs and outputs. In this case, you see I have like 2 outputs, and instead of 1, I have 0.1 and then 0.89. Now, you may be wondering, why don't I have 0.9? Well, because you have to pay a miner fee. And the miner fee is whatever is not implicitly defined, basically. It's whatever change is left over. So the input plus the output plus the miner fee are always equal to each other. So I basically gave the miner 0.01 Bitcoin, which is a lot, good Lord. The fee for the miner is the sum of the inputs minus the sum of the outputs. Once you put in a whole block, but that's the basic math. So what's funny is if you were to screw up, and people have done this, you would have to do it manually. I don't think a wallet would let you. But let's say you went to pay someone 0.1, right? Well, you get the change. Like, you want the change left over. So if I'm paying someone, I'm paying them 0.1. The second address is the change address. So this is how much I get back. If I left this out, all right, imagine this isn't here. What would happen? You would just be giving 0.9 Bitcoin to the miner as a fee. Because no matter what, this has to hold up. You can see here, I just show another example where instead of, you can have multiple inputs, and again, each input came from a different block. I gave it different names, XYZ, 3, 4, 5, DEF, 1, 2, 3, and then you have various outputs. So I just want to give a general kind of layout of what these UTXOs are like, because they're a lot like a $5 bill. Like, when you spend $5, you either spend the entire $5 and get nothing back, or you get change, and that change needs to be defined. In this case, maybe these are both yours and you're paying 3 different people, and then this is your change. All right. And then this is a little graph I made just to show you how complex, the inputs and outputs of the UTXOs can get. I mean, you could have tons of inputs, or you can have a bajillion outputs. anytime an exchange pays you, or if you transfer funds from an exchange to your own wallet, they always generally look the same. There's like one or two inputs, usually just one, and it's huge, has like hundreds of thousands of dollars, and then it has like 1,000 outputs. It has tons of outputs because they're just paying out tons of people who just did exactly what you did. So that remains to ask the question is fundamentally from a programmatic perspective, because I'm assuming if you're watching this, you're like, you know what, I have no idea what this funny money is, or maybe you're interested. You still may be asking yourself, well, what really is a Bitcoin? You know, I know, I don't know about you, but for me, for a while, I just thought of a Bitcoin as a spinning Mario coin, So what really is Bitcoin? What happens when you actually buy Bitcoin? Like, what do you physically have? All these Bitcoiners are running around saying you have this, you have that, and they're throwing analogies. But fundamentally, what do you have? Well, all you have is an address and a number. And that's wrapped up and it has a transaction ID, which is, you'll learn and we'll go over in a second, is a hash of all this. But how does this number belong to me? Like this isn't what's called a Bitcoin address, but it doesn't have my name on it. It doesn't have my social security. Like, how do I prove to other people that it's mine? How do I claim it's mine? How does someone not just steal this? Like, this is still very kind of confusing. Well, and this is another point I'll bring up is a lot of people have this notion of, let's say every 2 weeks I get paid and I put $50 into Bitcoin. So here's 2 weeks, 2 weeks later, 2 weeks later, 2 weeks. Yeah, these are all $50. So in total, I have $200, right? Now my wallet, just to be clear, a wallet is a piece of software that reads the Bitcoin network and it knows what blocks, what transactions you control. The wallet says I have $200. And I know I have $200 because I bought $50 worth 4 times. But that doesn't mean there's some magical variable on the Bitcoin network that has my name and has 200. No, really, I have just 4 transactions, and I have 4 addresses that somehow are mine, that I can prove that are mine, and I can claim ownership. I'm about to go over how I can do that. But I just want to show you that it works like this. This isn't a ledger-based this isn't a ledger-based blockchain, kind of like Ethereum, where there's these global components. Everything is UTXOs. Everything is transactions. Oh, a lot of people, again, really get caught up with the decimals. I can't tell you how many people literally don't want to mess or buy Bitcoin because they can't afford it. And of course, you tell people like you don't have to buy a whole Bitcoin. Bitcoin is divisible by 100 million Satoshi. So in other words, you can go out to 8 decimal places. The problem is this isn't very appealing. People are like, well, I don't want to own 0.00125, and this really doesn't have anything to do with finance. It has to do with human psychology. No one goes around saying, here's my baby, it's 0.375 years old. Like, no, you go by weeks, whole numbers, and then you go by months. And then eventually, usually around 15, 16 months, the mother suddenly decides we're going and rounding into years. And then everyone goes by years, except for kids. Kids are very, kids, they won't use decimals, but they'll use fractions. I'm 4.5, I'm 4 3/4. But you'll never hear a kid say I'm 3.625, So I just mentioned this because in reality, you can, instead of thinking of it at 0.00125, you can think of it as I have 125,000 Satoshis. That's pretty cool. I mean, most people have no problem having 125,000 of anything, and most wallets, you can change it from BTC to Sats, and in actuality, here's the number 125,000 written in binary. This is actually what the number 125,000 looks like in binary. On the blockchain, when your amount is recorded, it's not recorded in Bitcoin. So if you have 1 Bitcoin, it doesn't say the number 1. It's literally written in hexadecimal, the number 100 million. So it's actually recorded in the amount of Satoshis. Bitcoin is just the large denomination. Of course, the reason why Satoshi did this for several reasons, but first is A Satoshi is only worth, a hundredth of a cent or whatever. Actually, you know what? Let's not do that. Let's just do it. So if Bitcoin's $30,000 divided by 100 million, that's how much. Now, if you can imagine in the beginning, if you always went by Satoshi, you could say, oh my gosh, in the last 10 years, Bitcoin has gone from 0.000000001 and now it's all the way at 0.0003. Oh my gosh, that's amazing. Like, no, that's not really exciting and it's not really tangible. Now, granted, it's the same thing as saying Bitcoin went from $1 to $30,000, but you're using larger denominations. But again, I just mentioned this for any of you that have been scared of Bitcoin because owning a fraction scares you. If owning a fraction just annoys you for whatever reason, just go buy Satoshis. So once again, what do I have when I own Bitcoin? If I bought Bitcoin right now, all I would have is an address with an amount attached to it in Satoshis. But whatever, let's ignore that for now. How is this address mine? Like, how do I have ownership of this? Like, where's the magic? And that's where cryptography comes in. And really, cryptography is simply the most simple way I can put it is it's leveraging a math problem that's easy in one direction and hard in the other. Well, what does that mean? Well, the classic example, which most of these algorithms are based off of, is the discrete logarithm problem. Well, what's that? Well, it's simply this. If you take a really large prime number and you multiply it by a really large prime number, you get a really big number. This is very easy for computers to do. Now, when I say large, I'm talking about a number that has, 77 digits. We're talking about a number in the realm of how many, atoms are in the universe. These are very big numbers. But despite to say, computers have no problem multiplying these very large numbers. All right? And here's an example of a really, really, really large prime number times another really large prime number that would likely be done on Bitcoin. It's 100,000 trillion, 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 trillion. Or the actual name is 498 quattrovigintillion, But here's the issue with cryptography. And this is where the discrete logarithm problem comes in, is if I were to give you the very, really big number, and I ask you to tell me, what two large prime numbers multiply to give you this number? This is a hard problem. Now, when I say hard, I'm not using the word hard as like an adjective, like this is very hard. I'm saying hard as in mathematically hard, which means there exists no algorithm. There is no shortcut. There's no short path to solve this problem, which is why it's called a problem. Meaning the only way you can do this would to be to check and guess, to guess every single number combination possible in order to get this number. Now, as you can imagine, that would take, every computer in the world all hooked together tens of thousands of years to solve. And that's the essence of cryptography, is backing things up, which you'll see in a second, protecting things by a problem that's really easy to do one way. It's really easy to encrypt, right? But very difficult to break, simply because there's no shortcut to this answer. So hard means there exists no algorithm or shortcut to find the answer. The only way to find the answer is by brute force, guess and check, all right? Numbers are in the range of atoms in the universe. These are very big numbers. So you start with a private key, all right? Many of you have heard private key, public key. What the heck is a private key? Well, you could think of a private key really in two ways. Really what it is a super long, evil password from hell that you would never want to memorize. I mean, we all know, we got to do an uppercase, we got to do a lowercase, we got to do a number, we got to throw in some symbols, because it's got to be very unique. Well, this is, suffice to say, a very, very, very unique long password. But what a lot of you may or may not know is that passwords are just numbers, right? Remember, cryptography deals with numbers. So how is this password a number? Well, it's really quite simple. You just have an encoding table. So somebody decided, in the beginning of computer science that, all right, A is 0, and then we're going to go all the way to Z. Z is equal to 25, and then lowercase a is 26, and everything just has a value. So if we were to take like KWU, it'd be really straightforward. K is 10. All right, W is 48, and then U is 46. And then we convert those numbers to binary, put all those binary numbers together, and we get a really big number. So you see, just with 3 letters, we get the number 44,078. If we were to continue this with every single letter across and then slam them all together, we're going to get 256 of these ones and zeros, and then we're going to end up with what I showed you in the previous slide. 100,000 trillion, 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 a really, 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 really big number. So a private key is just a number. Is a very big, unique number. And that's where everything starts. So we start with the private key. The next step is the public key. So the public key we derive from the private key. And the public key is, once again, just another really big number. There's a little bit more to it than that, but how do you derive this? Well, the way you go from the private key to the public key, and again, this is crucial, remember, it's very easy to go in this direction, but it's impossible to go in this direction. So this is very important, is if someone has your public key, this is why it's called public, there's no way they can derive the private key. Why? Because of that problem I just showed you, the discrete logarithm problem. You cannot go the other way. It is too difficult. So this is crucial. This is the one-way function. Public key, you can share whatever. Nobody knows the private key, but the private key is the one that can come up with the public key. All right? Now, how do we get from here to here? We do it using what's called elliptical curve cryptography, or ECDSA. Now, how does this work? Quite simple. It's actually pretty straightforward. So you have a curve. This is the elliptical curve. This curve actually has an equation, y equals x squared plus y something. I don't know what it is. But the math is really simple. In order to calculate the public key, you take the private key, which is a number, all right, and we put that as a point on this curve, and we multiply it by another number, which we'll call g. All right. Now this g number is fixed. It's the same for everyone. All right. So this g could be, it's a really big number, but let's just say it's 25. All right. All we do is take the private key and we multiply it times g, and that's the public key. So wait a minute. I'm no math genius, but if I'm solving for x, okay, you told me if the public key is known, there's no way in hell you can know the private key. If I'm solving for x, don't I just take the public key and divide by g and get x? Well, that's why we use elliptical curve, because the way you multiply points on a curve is not how you do it in regular life. And suffice to say, it's impossible to go the reverse direction. So I just show you the curve to kind of give you a feel and to show you like, hey, it's really easy to go from here to here, but it's nearly impossible to go from here to here. All right. So that's elliptical curve cryptography. Now the public key gets turned into what's called an address. All right. You can call it a public address. And this is, again, a string of characters. Generally speaking, it's going to be shorter because we don't need to have it as long. But again, same thing. You can only go this way, not this way. So if you have a public address, it is linked directly to a public key. If you show someone the public key, they can instantly verify that this is the address because, again, arrow going this way, super easy. But if you were to have an address and you asked anyone what public key made that address, it would be impossible. So how does this happen? This is where the hash comes in. The SHA-256 you hear so much about. This is the most common hashing algorithm developed by the NSA, the government. It's used on every secure website. It's used everywhere, all in security. This isn't like a Bitcoin specific thing. But what is a hash? All right. I'm about to demystify that because, again, the biggest notion you hear is that a hash is a complex cryptographic puzzle, which is a horrible analogy. It's just horrible because I don't know about y'all. When I first heard that, I was like, what is are the miners doing Sudoku, and solving crossword puzzles? Like, what do you mean a puzzle? And that's not really what a hash is at all. So a SHA-256 stands for Secure Hash Algorithm, 256 bits. All right. Now, the best way to describe a hash is I want you just to think of a magic box. All right. Here's a magic box. It has an input and it has an output. Well, you don't know what's in this box. All right. It just has a label. So let me tell you what this box does. You could really think of the box really as a super number shuffler. I mean, that's really the best analogy. So let's say I have a whole bunch of ones and zeros, all right? I have a whole bunch of data. If I put it in this box, what comes out? What comes out is 256 completely scrambled bits, all right? Completely unique to this data. What happens if I put in 1,000,000 bits? All right, obviously, you're going to hash like a whole block, and a block is 1 MB, which is 8,000,000 ones and zeros. If you put that in this box, what comes out? Once again, 256 unique bits. Now, that's where shuffler is a little bit of a stretch, because if you shuffle 8,000,000 bits, you should get 8,000,000 bits. No, it's shuffling and throwing stuff out, because no matter what, you always want to just have 256 of the output. All right. What happens if I put in just a zero? Well, sure enough, you're going to get an absolutely unique string of 256 bits. Generally it's not written like this. It's written in hex. So usually you'll see some letters in there, A, B, C, D, E, and F, but I'm just showing it as the actual bits. Well, again, just to drive this home, what happens if I were to put 0 in again? And this is where some people get confused. If I put 0 in again, I'm going to get the same exact output. Okay, so again, you may be thinking number shuffler, right? Imagine taking a deck of cards, and you imagine throwing it on the ground and taking your hands and shuffling them all over the floor and putting them back together. That is pretty random, right? But if I were to give you a deck of cards and to tell you to do that once again, the cards would not be in the same order. That's not how this works. This is highly sophisticated, and it's more like taking a deck of cards, cutting it up a certain way, and following a very strict steps in order to move the cards around, and to do something so fancy with the cards that you always can get something super random as far as the ordering of the cards, but it's always going to be the same unique ordering. So the output is 256 bits that is absolutely unique to the given input. This is crucial. This is the whole point of what a hash is. A lot of people don't understand, like, why do I even have a hash, which I'll tell you in a second. But this data, whatever it is, this is a unique set of data. When you hash it, you're going to get 256 bits that's absolutely unique to that set of data. If you were to change that data at all, add one more 1 or one more 0, you're going to get a completely different hash. So really, the output is completely deterministic. Deterministic means you can determine what it's going to be, always. Like the 0 will always give you the same string of 256 bits. You will always get the same output for a given input. The process is impossible to reverse, which this one, it seems to kind of be common sense, because if you put in, the whole Google Library of Congress, a terabyte of data, 1,000,000,000,000 ones and zeros, and you got just 256, which is unique to that set of data. Well, it goes without saying that you can't go from 256 zeros and ones and somehow go backwards and create 1,000,000,000,000 zeros and ones, But that's just to say this process is impossible to reverse. And by all accounts, seems to be quantum resistant, but that's not proven. But I just thought I'd throw that out there for you super nerds, So really, a hash is just like a fingerprint. It's like a piece of DNA. I mean, everyone knows a fingerprint is what? I mean, it's an image, but obviously we know computers can break it down into a piece of data. Basically, a computer can break down your fingerprint into literally a string of ones and zeros. That's what all our phones used to do. And that is completely unique to what? You, because you have a unique fingerprint. That's precisely what the SHA-256 or a hash is doing. It's giving you a unique fingerprint, DNA, however you want to think of it, for a certain set of data. In the case of a fingerprint, you are that piece of data, because it's unique to you. Or the DNA is unique to your blood, unless you're an identical twin. So with that in mind, now we can really begin to understand how this all works. So with transactions, we have private key, public address, which I described, and we also have one more thing called a digital signature. Because obviously when you spend Bitcoin, you have to sign for it. And this is probably a really good name because just like you sign for something in real life to verify that you looked at it, it's the same thing in the digital world. But the difference is this is something completely unforgeable. This is something you can't fake. You know, someone can fake your signature. Someone can fake Michael Jordan's signature, but you can't do this in the digital world. And you'll see why. So, private key. So first I want you to think of a text document and imagine that you want to send this secretly to a friend. Well, you want to encrypt it. So the private key, generally in the general sense, what a private key does is it encrypts data. So you can take this data and imagine it encrypted. And most of us are familiar with this. It's scrambled. It's in your secret code. So the private key encrypts. And then you send it to your friend. All right? And your friend has the public key. Well, what is a public key? The public key, the best analogy is the public key decrypts the data. So your friend uses the public key to decrypt so they can read your note. Now, you'll see very quickly that, again, the analogy of a key kind of falls apart because we all know what keys are, and we know keys can lock and they can unlock. You just turn it left or turn it right. But in this analogy, no. Imagine a key that only locks something. It never can unlock. It only locks. And then imagine another key that only unlocks. That's all it can do. Anyone that has this key, all they can do is unlock messages from you with this private key. So they're one-way keys. Private key encrypts, public key decrypts. All right. With that being said, we have all the information we need to now understand how a transaction works. All right. So we'll start with us. This is our money. This is our Bitcoin. We have it, right? We're not sure how we have it. Doesn't have our name on it. Doesn't have any ID, right? But let's just go to say that this is ours, and we're going to give it to our friend. We're going to give him all our money in this transaction. I'm not sure why, but we are. So what do? We go in our wallet. All right. Our friend gives us his address, and we send this amount. The wallet constructs this transaction. You know, it says, hey, the input is this is your address on the blockchain. It gives it a transaction ID, which is a hash. Remember what a hash is? So it takes all this data and hashes it, gets something completely unique, and converts that to a string, and that's the transaction ID, you know. And then what we do, sorry, that's us, and we're paying our friend. We're Bob. It's always Bob and Alice. Our name is Bob, and we're going to pay Alice, all right? Bob and Alice. This is the hash of the transaction. All right, so first thing we do is we take this transaction ID, which is just a hash of all this, and we encrypt it. Remember, what does the private key do? It encrypts data. So we encrypt our XYZ321, and we come up with the digital signature, which I'm going to call HIJK123. That's our digital signature. Now, in order to send this to the Bitcoin network and have it be accepted, all we need to do is send three things. We just need to send this transaction, all right? That's this, orange. We need to send the digital signature. This is the signature showing that we signed off on it. And we need to send the public key for the address. That's it. All right, just go ahead and pause the video and see if it all comes together. All right. Now I'm going to walk you through it, but it's all right there in front of you. I constructed this transaction, right? I gave this address. I pointed to this, which I'm claiming is mine. But how do I claim it's mine? Well, I have my private key, right, which I'm not showing to anyone, and I encrypt this transaction ID and create this digital signature. All right? So the network looks at this transaction, and first the network says, you know what? Is this proper? You know, okay, input ABC. Okay, is that real? Yes, it's real. Is it really one? It is one. Okay, and you're sending to this address. Is this address formatted correctly? Yes. This transaction ID, is this really a hash? Well, let me see. I'm going to take this data here, hash it. Oh, they're equal. Okay, we're good. And then it gets a digital signature. And it's like, okay, what do I do with this? Well, you also gave it the public key, right? What does a public key do? It decrypts the data. So it can use this public key to decrypt the signature in order to get XYZ321. So now the network knows that you have the public key that belongs to the private key that encrypted this message. Now, we don't know that it's specifically yours yet, because remember, people reuse addresses all the time, and when you reuse an address, that means the public key is visible, so anyone could have the public key. But then there's the third step, and that is, what does the public key do? What is this address? This address is a hash of the public key. So the next thing, since we know that this public key was definitely, it definitely belongs to this digital signature that was encrypted by this particular private key, then we take this public key and we do what? We hash it and we connect to the address. So logically, only the owner of the private key, which was never revealed, only the owner of the private key could have encrypted this transaction to give you this digital signature, which is then unlockable by this public key. And we know this address belongs to this public key because this address, this public key, when it's hashed, equals to this address. So it's all chained together. All right? I'm going to move on, but if you need to rewind and watch that again several times, you may need to. That's how encryption works with transactions. All right? But again, none of this is revolutionary. This is not what Bitcoin revolutionized. This isn't what Satoshi revolutionized. This was established back in the late 90s. The cypherpunks had already worked this out. And this is very similar to how banking transactions happen on our online banking. Like, this isn't something new. I'm just describing to you how digital signatures work, how private and public keys and addresses allow you to prove with certainty that you are the owner of something, that you definitely approved it being sent to this person, because only you could have encrypted this transaction in such a way that this public key that definitely belongs to this address could have decrypted it. So it's all linked together. So now you should understand at this point how you can maintain ownership over a random strings of numbers, letters, and uppercase and lowercase letters. This is how you do it. But what the heck is the Bitcoin network? Again, the easiest way to think about it is how the centralized bank works now. Like, we have a computer. Remember, we have a ledger. We have balances. So I go and spend money, and the bank goes ahead and updates the ledger. Everyone is connected to this central entity. Everyone's connected to the bank. And it's the bank's job to make sure that all these transactions are updated correctly, that nobody spends more money than they have. And then if you do, actually, well, nowadays it's different. The bank wants you to spend more money than you have so they can charge you overdraft fees. But in the perfect world, they would just make sure that, John can't go ahead and, pay someone $20,000 when he only has $125 in the bank, Now, let's contrast that with a decentralized network. So now we want to get rid of the bank. Screw the bank, all right? So if we say screw the bank, I no longer want everyone to be connected to you and to be dealing with our transactions with you. Instead, everyone's going to run their own computer, all right? They're called nodes. And all those computers are all going to be connected to each other. All right, across the whole world, we're going to have thousands of nodes spread throughout the world, and everyone's going to be connected to each other, and they're going to keep track of the transactions that go on between them. All right, so again, what's the job of a node? The job of the node is to verify transactions, to store all the transaction data, and to make sure all the transactions follow the rules that we're going to set up. So now let's look at the difference. Now, let's say I go ahead and I'm on my wallet and I go ahead and try to spend some money. I send it to just the nearest node. I'm in Nashville and there's a node right up the street. He has a whole copy. He stores all the transaction history. He has a full copy of the network. He's like, okay, you're John and you're spending $50. All right, I'm going to go ahead and update your balance. You now have $75 left, and that's it. And then he goes ahead and shares that with everyone that he's connected to. And guess what? They all update their balances. and then they spread it out further, and they all update their balances, and they go further, and it propagates through the network across the world. Whether you know how the internet works, but it's just interconnected computers, and they all do the same thing. They're all verifying the transactions, they're all storing the transaction history, and they're all making sure that they're following the rules to make sure that nobody can cheat. Now, this in itself is pretty powerful because it's just with this setup, it's kind of difficult to cheat, or John to try to, because John could change his own balance and say, you know what, I actually have $10,000, but then the whole network would disagree with him, right? The double spend problem. Now, there's a lot of pros and cons that can go on with this kind of simplified overview. But the central problem, and it's the ones that the cypherpunks in the 90s were not able to solve, is the double spend problem. And if you look at the intro to the famous Satoshi white paper, that's really what he solved. I mean, Satoshi wasn't saying, I created a brand new form of money. Like, really, Satoshi was like, he said but we propose a solution to the double spending problem using a peer-to-peer network. That was really what Bitcoin was about. Now, of course, his solution to this double spend problem was end up being much more profound and end up obviously being so potent to the technology that we're about to get into. But everything kind of comes down to this double spend problem. So, without further ado, what the heck is the double spend problem? Well, the double spend problem, in the simplest terms, is a network problem, because we have a network of computers all connected throughout the world. So let's say you have $3,000, right? And let's say you open up a website to some company in New York, all right, Tiffany's, downtown Manhattan, I don't know. And you're on their website and you want to spend $2,500, all right? But you also go on Sony's website and you're going to buy a new PlayStation. With the same amount of money. You want to spend $1,000 at Tokyo. Now, remember, the network is distributed throughout the world. So in New York, as soon as you hit spend, it's going to connect first to a node, and most likely in the New York area. In Tokyo, Japan, it's most likely going to connect to a node in Japan. And therein lies the problem, is because when you process those transactions, so first he processed transactions for 2,500, these ones get processed for 1,000. Well, eventually, as it spreads throughout the network, that everyone's like, whoa, wait, red alert, red dot, like, what's going on here? Like, you're trying to spend it twice, when literally what's really happening is this: half the network saw the Tokyo transaction go through first. So half the network is like, all right, you spend $1,000, your balance is $2,000, right? And then a second later, they're going to get a transaction saying you're trying to spend $2,500, but you can't. That's invalid. The other half of the network, the other half of the world essentially, has your balance at $500. So basically, the double spend problem could be easily thought of as a networking problem that, due to time delays, will immediately fracture our network. Now our network is essentially not in sync. And how could it ever be in sync? How do we decide which transaction should have gone first? How can we solve this double spend problem? Well, I'll show you. It's really quite ingenious. So instead of receiving transactions and immediately processing them, instead we're going to take all the transactions and we're going to place them in a queue. All right, and we're going to sort them by transaction fees. That's what the mempool is. Okay, so we stack them, transaction fees highest on top. Now, why do miners do that? Because obviously they want the most fees. So you're going to put the highest fees on top. All right, and then we're going to create a block. All right, we're going to give an arbitrary size 1 megabyte. All right, and we're going to squeeze as many transactions into that 1 megabyte block as we can until the 1 megabyte block is full. All right, so now you're seeing what a block is. All right, now everyone on the network does this. All right, so now instead of everyone processing transactions as they come, everyone's putting them in a pool and they're forming a block and they're putting that block together. All right, let's just follow through with this idea. Now, at this point in time, you would have to understand at any one instant in time, as everyone does this, not all the blocks are the same. Obviously, the blocks in New York and all the nodes that are close to New York have almost identical blocks, but they may have one or two transactions that are different because it hit them first. You know, obviously, you may have a lot more that are different in Tokyo because it got transactions that haven't yet made it over here. All right. So now the question remains, okay, well, first of all, if we do this, this basically solves our problem because if we process things one block at a time, then we never have to worry about this double spend problem coming up. But now the question remains is, okay, how do we pick the blocks? What's fair? Which block should we pick first? Is it a first come, first serve? Is it random? Like, how should we decide who gets to get the block and therefore get all the fees? That's the real question. So, what's the incentive? Also, what's the incentive? Like, why would we even do this? Before, we got fees all the time. Boom, transactions came to us. Now, all the nodes are not getting paid. They're not getting any fees. They're coming up with a block and they just have to wait to get chosen in a lottery. Like, how is this going to work? Well, the first incentive is obviously if you get the block, you get all the fees. But in addition to that, you're actually going to get a block reward. So you're basically going to get paid initially with 50 Bitcoin. Now, I'm going to go into this further, but this is basically how Bitcoin is created. It's created block by block. But that is the first thing, is you want to incentivize people for doing this because it takes work, it takes energy to run a computer, so you want to incentivize that. So how should we decide who gets the block? Well, since you're earning money, then you should work for it and prove it, right? Like, how do we get paid? We get paid because we work. We work over time. Most of us is 40 hours. So when we get our paycheck, it is proof that we worked for 40 hours. Satoshi thought, why not do it the same? Since money is all backed up by work on every level, even gold takes tons of work and energy and mining to go in to create that gold. You're going to have to give me what's called a proof of work. So how does proof of work work? All right. It comes down to a hash. Now, again, in simplest terms, we're going to go ahead and take the whole block, right? And we're just going to hash it. Now, we'll go into later how we actually don't take all the transactions and hash them this way. We hash them in a structure, what's called a Merkle tree. But for all intents and purposes, it works exactly the same. So I'm just throwing that out for you super nerds. But we take all the transactions in the block and we hash them. All right. This is actually 256 ones and zeros. So if you're ever curious about really what a SHA-256 outputs, it looks like this. Well, it's usually not written in binary. It's written in hexadecimal, so it doesn't look like this. It looks shorter and has letters A through F mixed in them. But this is a hash. All right. Now remember, let's just rehash. This hash is absolutely unique to this set of data. All the blocks, all the transactions is absolutely unique to this. All right. Now I'm going to go ahead and truncate it. I'm going to just add a dot, 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 add 80 ellipse because I need some more space. All right. But I didn't really change anything else. All right. So what would happen if I were to add a 0 at the end and hash it again? And what would happen if I asked you, what are the odds the hash will begin with a 0? Like, this hash didn't begin with a 1. It began with a 0. Well, we know, like I said, if you change this at all, it's going to change. So if you just add a 0 at the end and you hash this hash, you're going to get a completely random, unique set of ones and zeros because of the super number shuffler that we discuss. And let's say, oh, wow, look, it started with a 0. Okay, well, it looks like we only had to try once. But what if I were to say, what are the odds the hash will begin with 2 zeros? Okay, well, let's try a 1. No. Try a 2. Try a 3. I'm just showing the first sets of numbers. And I'm counting in binary. This is the number 3, and then 4, and then 5, and then 6. And all we're doing is taking the exact hash of this data, and I'm just incrementing numbers. And I'm appending them to the end and hashing the hash again. And I'm going to keep doing that until I get my answer. Oh, 2 zeros. So it looks like it took me 8 tries. All right. What are the odds the hash will begin with 10 zeros? All right. In this case, it took me 4,126,456,135 times. You know, and this is a more appropriate example. And in essence, this is what took Satoshi's computer about 10 minutes to solve. Now, this isn't the number. I'm just throwing out a large number. But Satoshi, when he first started in the very first block, the number, the difficulty, this is actually called the difficulty. Sorry, I'm jumping ahead. This number here, this number is the proof of work. All right. And this proof of work is what's going to go into our block. We want to add that into our block. Now, pause. Why is that? Because that's the proof that somebody did the work. If you give anyone this block of data, the first thing they can do is confirm all the transactions, right? They can hash it, takes 2 seconds, and get this complete set of unique ones and zeros. Then they can add on your proof of work and hash it again, and they can see the results and say, hey, does it begin with 10 zeros? Yes. So with this, the proof of work is this small little piece of information that proves to the whole network that you did the work. You guessed 4 billion times by hashing a number with a hash until you got the result. And so this right here is what's called the difficulty, which I guess we'll get into the next slide. I haven't done these slides in a while. So as soon as someone does this, they're like, woohoo, I won, I did it. I got the golden ticket, and the rest of the network, everyone's doing the same thing. Everyone's doing the same process of taking their block, hashing it, and adding numbers and hashing them again, all trying to get them underneath that difficulty level of it begins with 10 zeros. You did it first. And as soon as you did it, you're like, hey, here it is. Here's my proof of work. And you send it out to everyone. And everyone's like, all right, fine, let's see. And everyone can check because, again, most people have 99% of the same transactions already verified. They go ahead and double check your block, make sure it's all legit, everything's lined up. And then they hash it, takes whatever, half a second, and then they take that proof of work and they hash it with that hash, and they realize, oh, it begins with 10 zeros. You did do it. And then they pass it on, and then the whole network moves on. And everyone begins this whole cycle again. All right? So this is what's called the difficulty target. All right? This is a target set initially in the beginning for how many minutes it'll take to do this. So again, I'm just keep throwing out analogies because sometimes it helps, assuming it's a good analogy. But you could think of this, a SHA-256 really as just a random number generator, Yes, it's a super precise, deterministic shuffling of data to give you 256 bytes, but these 256 bytes evaluates to a number, and since it's completely random, it's shuffle, it's basically a random number generator. So you're basically having like a random number generator, and then you're adding numbers and generating. So really, the whole game is how many tries will it take for you to randomly generate a number smaller than the difficulty target? And that's what mining is, quite simply. Oh, and here, I showed this, maybe I skipped a slide. This is how you count in binary. See, you have 0, 1, and then for 2, you just move the 1 over, and you have a 2. All right, then you change the 0 to a 1, and that's how you have a 3. And then you just start over. You just move a 1 up. All right, now this whole pattern will repeat itself. 0, 0, 0, 1, then 1, 0, 1, 1, and then you move the 1 over, and you have an 8. All right, so just if you're wondering how to count in binary, that's how you did it. I brought that up because you can see how the preceding zeros, those are just fluffers. So a number in binary, you don't start counting it until you actually hit a 1. So you can see here, until you hit a 1, that's when you can actually start counting a number. After that 1, you can have ones and zeros all day, but it won't begin until you hit a 1. Because a lot of times people like to think of the difficulty as it begins with zeros. And that's technically true, but really it means is the more zeros you have, the smaller the number. And then I like to use the dice analogy because a lot of people get thrown off because the harder the difficulty, the smaller the number. So if you think about dice, if I say, you know what, anything you roll past 12 and you win, Well, shoot. I mean, we all know you could pretty much roll anything but double sixes and you'll win. But if I say, you know what, anything you roll that's less than four, you win. Well, shoot, it's much, much, much harder to win because you basically need to roll snake eyes or a two and a one in order to win. So the whole point is the smaller the number, the harder it is because your subset of numbers shrunk. So that's why when the difficulty grows in hardness, when it gets harder, the number shrinks. It gets smaller. And of course, as it gets smaller, more zeros appear in front. So that's a quick analogy on that one. So once again, proof of work, power, and difficulty. Because oftentimes you hear proof of work consumes so much power and so much energy, and in the most general simplistic sense, proof of work doesn't consume that much energy. It's just proof of work. I mean, that's all it is. The issue is that when you start out, so the Bitcoin network started out, let's say they all started out on these cheesy iMacs, 2.2 gigahertz Core 2 Duo. This is the power of a computer in 2008, and all the computers were guessing 100,000 hashes per second, and they're all trying to get to a number less than 900 billion. That's the difficulty target, and it took about 10 minutes, right? Now, and so this difficulty of the whole Bitcoin network would be 1, all right? It's the baseline. But like I said, you're basically just guessing numbers. I mean, if a miner is a money printer, think of it as like a lotto machine, and imagine to win the lotto, you just had to guess these numbers. And instead of paying for your lotto tickets, you could just produce as many as you want. Well, what would people do? Well, shoot, give me more computers. I mean, shoot, if I'm guessing 100,000 per second, with 2 computers, I'm going to guess 200,000 per second. And so they just grow and grow and keep adding on computers. And so as the price of Bitcoin goes up, because obviously if Bitcoin is really cheap, no one's going to spend thousands of dollars on computers to mine, a penny. But as the price of Bitcoin goes up, then the advantage to buying more computers to earn money becomes more apparent. The problem with this is we're going to have a very, very quickly, the block time is going to get smaller and smaller and smaller and smaller and smaller. Just doubling the computers, we'll get to 7 minutes, and then we add more computers, and then everyone wants to earn money, and then before you know it, the block time went from 10 minutes to a second. So how do we keep the block time at 10 minutes? Well, every 2 weeks we have a difficulty retargeting. All right, what does that mean? We make it harder. So this is straight up from the Bitcoin code. All right. Every 2 weeks, we set a new difficulty target. We take the old difficulty target and we multiply it by the actual time of the last 2016 blocks, all right, divided by 20,160 minutes, all right? In case you're wondering, this is how many minutes are in 2 weeks, all right? 10 minutes per block, you just chop off a 0 and you get 2016 blocks. So in essence, is if everyone started speeding up, right, and instead of taking 20,160 minutes, it took a lot less, right? Let's say it took 17,136 minutes because the blocks were a lot shorter than 10 minutes. Then we're basically get a much smaller number. So basically we're going to multiply our target times 0.85. So we're going to take 85% of it, and we end up with a new target, which is smaller. And remember, that's why I gave you the dice analogy. A smaller number means it's more difficult. So now we've raised the difficulty by shrinking the number from 900 million to 765 million. And as soon as we do that, the difficulty now would be 7, because it's 7 times harder, and then our block time would go back up to 10 minutes. So it doesn't matter how much more powerful the miners try to put power into mining this. Because every 2 weeks it's going to retarget itself. Now, shoot, I did leave out a slide, which I'll go back to real quick. And that is this. And I gave this analogy because, again, in the beginning, Bitcoin nodes did everything. Bitcoin nodes verified transactions, right? And they also did the mining. But you hear so often now, and it gets confusing, that there's miners and that there's nodes and that they're two separate things. And that's not, and that can be confusing. Because the thing is, mining is a very simple operation. But the thing is, you have to do a lot of it. So slowly over time, and maybe I should just finish with the slide I was getting to, because that's kind of what I was getting to. Slowly over time, that grew. So let's just go there. So in the beginning, you just keep adding on more computers, more computers, more computers. But in order to mine and hash more and more and more. But the CPU is it. This is inefficient because this is a central processing unit. You know, the Intel chip is designed to do everything. So eventually, someone put it on a GPU. You know, fun fact I just learned is that was the pizza guy. You know, who spent 10,000 bitcoins on a pizza because a GPU is a general purpose unit, and so you can get a lot more power from this thing. But again, it's not just one. Before you knew it, people did more and more and more and more. And this is where Ethereum miners, they just have tons of graphics cards and they're all doing the same thing, hash, hash, hash. They're doing this hash because they're trying to win this lottery. Eventually you get to an ASIC. All right, now ASIC isn't specific for Bitcoin. Oh my gosh, there's ASIC chips everywhere in all cars and every devices. ASIC is just a specialized chip for a special purpose. All right, so it's an application specific integrated circuit. All right, integrated circuit is a chip. These are all integrated circuits. Okay, so this is just application specific. So someone spent the money. A Bitcoin got to a price that was high enough where it was worth it to spend tens of millions of dollars to design a specialized chip that only does hashes, and it does it really fast. And then build them in these boxes and basically turn them into supercomputers, because these are supercomputers. Like this is the new one of the newer miners, S19 Pro, JS, whatever. It does 140 terahashes per second. There are 342 ASIC chips inside this box. Like that is a supercomputer. It's not just one chip. There are hundreds of chips. You know. So once again, all the miner is doing is this $10,000 box is taking a block. All right, it's taking a hash of it. It's guessing a number, it's hashing that, and then it's getting a result, and then it's checking. Hey, is this number I got small enough? Is it less than this difficulty level? And if it's less than the difficulty value, boom, you won. Congratulations. If it isn't, it goes back here and guesses another number. Usually it's just incrementing numbers. And it does that 140 trillion times a second. All right, and even doing 140 trillion times a second, one of these miners will never win you an award because the mining difficulty is so high, you literally need thousands of these, all working together, all guessing different numbers in order to win a block reward. The current difficulty, well, when I did this slide, was 24.37. Now it's actually at 30, but this is trillion. So what that means is the current difficulty target is 24 trillion times more difficult than when Satoshi started the network. Really, this should say 30 trillion times. And this is fun fact again, because ASICs get such bad reps, like oh they use so much energy. No, this is energy efficiency keeps getting better and better. This is the most efficient use of energy, and this is a slide from Bitmain. This is on their new the one they did to hash Ethereum. Ethereum finally got an ASIC miner, but you know, supposedly they're switching to proof of stake soon, so they'll kind of be pointless. But what's funny is they showed the slide of how power efficient they are, and this is a lot of power, 2,556 watts. But then they basically said that's compared to 32 3080 graphics cards. All right, now a 3080 graphics card uses 320 watts. So 32 of those at 320 watts equals 10,240 watts. So you can see how this is 4 times more efficient than just using GPUs. You know, I just thought I'd throw that out. And then here, of course, is the hash rate. This hash rate, it just is kind of exponential. It's probably easier if you look at logarithmically, and you can see the journey of CPU, GPU to ASIC. But we're at the point now where it really is starting to plateau out, you know. and this is why it's important to look at it logarithmically. And it's plateauing because we've reached the limits of technology. I mean, this chart here shows you when GPUs came into play, when they started using FPGAs. This is like the next step, a field programmable gate array. And then when we got to ASICs, and the ASIC started at like 130 nanometer, that's like Pentium 3. And then now the newest miners are at full out 5 nanometer using iPhone 13, 14, state of the art. So Bitcoin is at the cutting edge. Obviously, the iPhone and the top Samsung device are always going to be a year or so ahead. They're doing, I think, cutting right into 3 nanometer. But trust me, Bitcoin's right behind it because it has the money in the market. But that's why the evolution has started to slow down. And that's a good thing. That's a good thing for kind of miners, Now, last part is, let's go back to the block. All right. Oh, let me go back to what I was saying about the nodes. So going back with these nodes, when you have a miner, and I'm sure you've seen pictures where a miner has 100,000 miners in a giant warehouse using a megawatt electricity, right? All those computers are literally doing just a few lines of code on the Bitcoin node. In the end, if they win and they find a block, right, then they send it out to the network and they literally act just like any other node. Like, I have a node in the other room of my house, and it does everything that the node that the miner does. The only difference is mine verifies all the transactions, but it doesn't obviously do the mining because you need just what I described, massive computing power to do it, So this goes into a much deeper level of playing on the balance of decentralizations, because a lot of people will say, oh, the miners aren't very decentralized, and one can argue that, but it doesn't matter because you still need all the nodes. There's a balance of the nodes and the Bitcoin miners. And kind of one can't really exist without the other. It's very symbiotic relationship. The miners provide all the security, but the nodes are the ones that actually run the network. They're the ones that are processing all the transactions. Because there's far more nodes that are running out of people's houses than there are running at mining farms. Because when you take into account like a mining pool, it's using miners from across the whole world. But in the end, it's just one node that's doing the work, and all the miners are just sort of feeding into it. So I'll go into that in more detail on that in a bit. But to finish up our blockchain, so now you understand the block, all right? But we haven't quite understood the chain and how all that works together. So on top of the block, we have what's called the block header. That's that blank space up here, all right? And we're going to throw in the dates. We have some dates and times. We're going to throw the difficulty into the block because we're always referencing the difficulty to see if we did it, matched it with our proof of work. And of course, we're going to put the hash of the block in there. But when I told you that we're going to hash all the information, all the transactions, we're also going to do a little bit more. We're also going to include the hash of the previous block's transactions. All right, so this hash isn't just including all the transactions. It's including this 256 bits as well. It's including the hash of the previous transactions. All right, that is crucial. Now, why is that crucial? Well, it's really quite simple. If my slides will work. So this goes into the blockchain immutability. Again, you've heard this. You can't change it. Nobody can mess with it. Well, why? Because can you change or modify a transaction? Well, no. We've already established you can't, because if you change just one bit, if you flip 1, 1, or 0, this transaction ID will change, and so you'll invalidate the transaction ID. So a transaction ID is a hash of the transaction data. Any change to the data would invalidate the hash and vice versa. Well, can't you just delete a record? Can't someone just delete a record erasing payment? Well, I mean, you could, but what would you do? What would you do if you try reordering the transactions or swapping them with different ones? Any change to any transaction on this block would cause the hash of all the transactions to change. Anything. If you add 1 0 at the very end, the hash would change. If you modify and change anything about any of these transactions, this hash will change. This would in turn invalidate the proof of work and will force the attacker to redo 10 minutes of work on the block in order to find a new proof of work. Remember that 10 minutes of work was done on one specific hash. So if you change anything in the block, you get a new hash. And by all accounts, that proof of work no longer works. If you hash this hash with the proof of work, you will not get something that begins with 10 zeros. Now, granted, it's possible, but you have a trillionth of a percentage chance for that to happen. Next slide. Now, remember, they're linked together. So this hash goes into the next block at the top. So by consequence, this means that the hash of all transaction is no longer valid as well, since it was included in the previous block's hash. So if I change anything in a block, I change the hash. If the hash changes, you need to redo the 10 minutes of work to get a new proof of work that makes this block valid. After I do that 10 minutes of work, the next block that was created after it, this hash gets changed. It's a new hash. And the whole process starts over. Since this hash changed, then this hash with this data would give you a new hash here. And this new hash here won't work with this proof of work. So you have to redo 10 minutes of work on this block. A new hash would in turn invalidate the proof of work and force the attacker to once again redo the 10 minutes of work on the block. So in other words, proof of work builds into proof of history. Each block increases the proof of work required to make a change in the past. Time strengthens the immutability of the blockchain. This is why a lot of times you hear how, you need at least 3 confirmations. It used to be 6 confirmations, which sometimes was really large amounts. But the reason for that is if you're 6 blocks in the past, then someone would have to have well over 51% of the network's power, because if they try to change anything here, they have to redo 10 minutes here, 10 minutes here, 10 minutes here, 10 minutes here, 10 minutes here. They have to spend an hour. And by the time they spend an hour, guess what? The blockchain has grown by 6 more, so they'll never catch up. So they would need to have an overwhelming distribution of power in order to change any data on the network. Oh, tokenomics, and this is funny. Bitcoin's tokenomics are the coins are created with each block. They're always evenly distributed. All the other crap coins, they get handed out right away. Like Ethereum, insiders got 15%. You see it's crazy with other ones. Binance, 50% was all the insiders, venture capitalists. Polkadot, 33%. Cardano, 17%. Solana, 48%. And then you have tokenomics every 4 years. Again, every 4 years, the block reward goes in half, or 210,000 blocks. Why is that important? That's important because you always hear about the 21 million limits. Well, where does that 21 limit come from? Nowhere in the code is there a limit that says 21 million, at least not in the general sense. It's because after 4 years of doing 50 Bitcoin per block, you're going to have 10,500,000 BTC. You're going to have 50% of the supply. And then it's going to cut in half to 25. And 4 years of that, you're going to get the next 25% of the supply. You're going to have 15.7 million. And it's going to go to 12.5. Now we're in 6.25. And we're well past 87.5. By 2024, we'll be at 93.75. And we'll be at 3.125. And it's just going to keep doing this. Half, 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 half. By 2052, we're literally at 99.95% of all the Bitcoin being mined. It'll literally take to the year 2139 or 2140, well over 120 years. It takes that last 0.1% takes a century, because this halvening every 4 years is going to go until it gets to 1 Satoshi. So until it gets to 1/100 millionth of a Bitcoin mined each block for 4-year cycle, that's when it's over, because obviously you can't cut 1 Satoshi in half. So that gives you the 2 trillion. I mean, if we move the decimal over, you get 20,990,999.9769 BTC. So it's not quite 21 million, you know. So blockchain security, and this is the thing that a lot of people get caught up on, is it gets confusing because in the regular world, blockchain security, most security is like a firewall. You heard of a firewall, right? And everyone knows security works exactly the way you think it does. How do you secure something? You lock it up. You lock your car, you lock your doors. If you really want to get real good security, you lock it into a safe. You put it into a bank and lock it into a bigger safe. So you create these external barriers to stop something. Now, many naysayers have trouble wrapping their head around the Bitcoin and why it's secure because they understand fundamentally that this is flawed. We hear about it all the time where our information's leaked. Hackers got all our social security numbers. Hackers got into this. China hacked into the NSA and downloaded a whole bunch of data. Granted, it was encrypted. But we understand that these walls are built by men and they inevitably fail, and inevitably there's leaks. And even if those walls are bulletproof, right? Somebody runs it. Someone's got God mode access. There's a security person that has full access because these barriers are run by men. Now contrast that to the security of the blockchain. There's no walls. I mean, there's no firewall. There's no anyone can download the blockchain. There's no password you need to download. There's no admin mode. There's no nothing. It is completely naked and exposed. And as I described it, you should understand that it's completely backed up by hashing and simply by mathematics. A lot of times you hear that nobody can mess with the ledger, you know, but that is absolutely true, but not implicitly it's not true. Because I can download a block from the blockchain right now on my node. And I can go in and change a line. All right? I can change it. There's nothing stopping me. It's literally just a text file. But if I change something, all right, what happens? I change the hash. If I change the hash, I invalidate my proof of work. I then have to do 10 minutes of work using hundreds of millions of dollars worth of high-end ASIC computers to redo that 10 minutes of work. And then after I do that, I have to redo the next block, and I have to keep doing that. It's overwhelmingly against in your favor, and it's all really a matter of capitalism and economics where the hashing power and the amount of money it costs to do this in mining hardware and electricity, that's what prevents anyone from making changes to the blockchain ledger. So what is the weakness? I mean, everything's got to have a weakness, right? And in that sense, I would say, yes, there is a weakness. The Bitcoin blockchain itself is impregnable, right? But we just learned that the blockchain is made up of transactions. And transactions are just filled with addresses. And addresses are just validated by public keys and signatures. And public keys and signatures are all linked to a private key. All right? And here's the weakness, that the private key needs to be run through a computer. Like it just does. You know, you need a computer to deal with Bitcoin. Why? Because no one's going to go take this number and do the complex elliptical curve multiplication to get a public key. No one's going to do the complex mathematics to do a digital signature. You're going to need a computer. And a computer is susceptible to hackers. Your computer is connected to the internet. Everything about a computer has what? The general standard sets of security mechanisms, that being a firewall. You know, the computer that I'm running right now is a Windows computer, and this is how its security works. And it's still susceptible. For all I know, I have malware on my computer right now, and someone's spying on what I'm doing. I don't know. But now that's linked to, they have access to possibly my private key, and therefore they can get access to all my wealth. This is what a hot wallet is when you have a private key on a computer, on a wallet that's on a computer. No matter what, if that data is stored on a computer or any type of machine, cell phone that's connected to the internet, it's a hot wallet. And that's where hardware wallets come into play. I'll just give the example of the ledger. This is the first one I ever got. I got like a whole bunch now, treasure and a cold card. But a ledger is a basic little device. It's got a little tiny screen and it's got two buttons. All right. It uses Bluetooth to send information to your phone. This is a picture of the treasure. This is the keystone. It kind of looks like an Android phone, but it doesn't have any Wi-Fi chips or no way to connect to the internet. Supposedly, honestly, I don't trust these ones. I don't even know why I showed the picture. And there's a cold card. All different kinds. This one looks like a dang calculator. This one's got a little touch screen. Looks like a little tiny phone. And then you have this one. It's like a little tiny 80s Atari video game. You know. Oh yeah, I pointed this out because you see how the numbers are all shuffled. Because you wouldn't want someone to watch you type in your PIN because they could possibly know what your numbers are. They have a feature on the cold card that does the same thing. So, thought I'd throw that out there. But what is this? Well, basically, it's a computer. It's a specialized little computer. It's got a government grade encrypted chip. It is the most simple computer you could possibly devise that has one purpose. And that purpose is to store your private key and to do the things you need to do a transaction. So, for example, it holds our private key. Our private key is stored in a hardware inside this chip. All right. And then when we're ready to do a transaction on our phone, let's say I'm going to pay someone and I make a transaction, I go ahead and send that transaction to the ledger. Not a big deal. It's public. And the ledger uses my private key to go ahead and send the digital signature. It goes ahead and sends the public key. This is all public information. And now I went ahead and spent my money. And what did I do? My private key never was susceptible to hackers. It was never touched to the internet. Now, yes, granted, this is still a mini computer, but now someone has to physically get a hold of it to do anything to it. So there's a big difference in that, So in the end, you got to trust something, So this is kind of like the most minimal piece of trust is keep something really simple, really offline, no one can get access to. The whole point is to protect your private keys, and this particular one uses encrypted Bluetooth. So essentially, we've converted our digital private key into a physical key. That's really what we did. We have a physical, something we could hold on to. All right. So Warren Buffett, listen up, because the biggest issue you're having is, it's rat poison and it's nothing real. Like, no, this is something real now. We've turned a physical device into a physical manifestation of a key, which we can then access our digital wealth. Does this key have any security? Well, yeah. I mean, it's got a basic PIN code. Now, you don't want to use your standard PIN code. You want to make something unique. But most of these hardware keys are really strict. The ledger only gives you 3 PIN code attempts, and then it deletes itself. It wipes itself, Or you can enter a decoy PIN to access an alternative wallet, What if you're, again, under duress and you want to enter a PIN? Maybe you have $1 million and you put $100,000 into a decoy account. So, hey, at least the thieves can get off with something so they don't kill you. That's what a decoy is. There's also decoys that will do time locks, where you can enter a PIN that'll automatically lock it. I'm like, oh, man, I'm locked out for 24 hours, Or you can have a self-destruct PIN. The cold card has a PIN that you enter in once and it will self-destruct. Now, it doesn't do it like Mission Impossible style where it's like smoke or something coming out, but it literally self-destructs and becomes inoperable. Also, it gives you more attempts. It gives you 13, but that's all you get. After you get all those attempts wrong, it self-destructs. It does not reset. So a cold card, if you forget the PIN code, just forget about it. You got to buy a new one and start over. You can do time delays between attempts. Oh, the cold card also has anti-phishing words. This is a fun security where one of the top ways that maybe someone could attack a hardware wallet is by using the evil maid attack is what it's called. And essentially, what if you have a friend who's like a thief, and he's trying to get at your wealth. So he has a ledger, but it's a fake ledger. It's a ledger that just allows you to enter PIN numbers, and it doesn't ever go anywhere. It saves the PIN number and sends it to the hacker's phone. So he swaps out his ledger for your ledger and then says, hey, send me some money. And then you take out your fake ledger because he swapped it when you weren't looking on your desk, and you're entering your PIN, and you basically instantly gave him your PIN. You didn't even know it. And then your friend looks at it, you're like, gosh, my ledger's not working. And he swaps it, swaps the ledger back with you. And then you're like, oh, it works now. Okay, here, I'll send you $50, blah, blah, blah. But the hacker now has your PIN code. So, he can go ahead and get your ledger back again, and then he can steal all your funds. That's no fun. On a cold card, it makes you split up your password in two segments, like 1, 2, 3, 4. Let's say that's your password. Bad idea. You put in 1, 2, and then it's going to show you two absolutely unique seed words that are that you will only see on this particular cold card when you enter 1, 2. So every cold card in the world, if you enter 1, 2 and hit enter, they're all going to see different two words. Maybe you'll find someone that says enjoy top, but they're in a different order. So it allows you to, if someone tries to phish you or do an evil mate attack and switch a cold card with you, you'll know immediately when you put in your passphrase, because you're like, wait a minute, those aren't my words. My words were penguin and hat, not top and joy. Like, immediately don't even put in the rest of your passphrase. It's also air gapped via micro SD. So for people that don't even ever want to have a cable from a computer touch their cold card, because USB cables can be infected with malware, pretty potent malware.